So yeah, so today should be so categorical trace. So I think in the abstract I proposed 1 plus 2, which is not quite the same as 3 when you're talking about higher categories. But kind of before going to that, I kind of want to spend a bit more time on the trace on the Hecke category, which I talked about yesterday, because there were more things and kind of, you can say, okay, you can kind of recover more or like explain a bit more than Lusztig theory in terms of this language, and so kind of I want to spend a bit more time on that. Okay, so to recall the setup of yesterday, so we had G over FQ bar with the Frobenius, which comes from some FQ structure. We have a Borel pair. I don't think I said yesterday that we fix this Borel pair to be Frobenius stable, but and the Frob. Okay, and then we had H, which was this Hecke category. This. So I'm going to say free monodromic. And it's a variant of the co-free sheaves that appeared yesterday when talking about Bezrukavnikov's equivalences. So the free monodromic Hecke category, so and maybe finite Hecke category, finite as opposed to affine. Whoops. Okay, and so it was erratic sheaves on G mod U mod U, which were monodromic and taken and completed in this sense of Jovian. Okay, and so then the statement was that trace of Frobenius on the two category of modules over this theorem is equivalent to sheaves on the twisted adjoint quotient. So, and this is the same as D of rep G fixed by F. Okay, and so I sketched kind of the way you compute this thing, and so kind of if you recall, so this was H tensor H Frobenius over H tensor H rev. Rev should be written here, and it was kind of the totalization of some category. And so let me just rewrite one of the lines that were yesterday. Sorry, so let me just put my notes. It's not this one. Okay. No, this one. Okay. Okay. So the first time was kind of sheaves on G mod U mod U, and so the way divided by at Frobenius of T, and the way we obtain that is that we rewrite a resolution of the first copy of H. So this one, in terms of some bar complex, we unravel what this is, and then kind of we can just use some kind of Kunet formula to compute this term. Okay. And then there were some kind of partial convolution maps from G mod U T, G mod U T, Ft, and so on. Okay. And okay, and then it turns out that this was the same as sheaves on G divided by at Frobenius of G. Now there is a natural map from H to this thing which sends X to 1 tensor X. And kind of this first term here, like in terms of what it was H, so for the torus, tensor over HT, tensor HT, with H itself, and so this first category here, and this map here is just the inclusion onto this first term. So and kind of. So let's call this map small t. Is the inclusion of the first term. And the point of doing that is that so we can compute what this corresponding map is. And so we have the following diagram that shows up, and I think that kind of showed up a bit yesterday as well in the questions. So the Hecke category is a certain category of sheaves on G mod U mod U. So we first go to this quotient here, and I will comment on its structure in a minute. And then, so if you recall, so the first step was to pull back from G mod U divided by ad frominus of t down up to G mod ad frominus of p. So we can plug that in the diagram. Okay, and we could do the same for you here, and this is Cartesian. And both guys here will map down to G mod ad Frobenius of G, which is the thing we care about. Okay, and so let's call these maps alpha, beta, and pi. And so the claim, the lemma, which is a corollary of the calculation, is that the map, there is an isomorphism of functors between t, so of functors from h to sheaves on G divided by ad frominus of G, of functors between, so pi lower shriek, alpha upper star, and beta lower star, and so it's the same as beta lower shriek because this is proper. Hopefully I am not missing a shift. Maybe I am, and if so, I am sorry. Okay. Okay, and that's kind of the main input to relate this to classical Deligne-Lusztig theory. So just let's recall. So a classical Deligne-Lusztig theory. So what you do is you choose W, some element in the Weil group, choose W dot, a lift of this element. And you can form these two varieties. So X of W, which is a set of Borels in relative position W with their Frobenius translate. So that's a subset of G mod B. And some cover Y of W dot. And G mod U. Okay, and these two things carry an action of G fixed by F. Sorry. And the top one carries an action of T fixed by WF, which is the group of rational points of a torus inside of G. I am missing a B here. Okay, and then so the main object of study is a cohomology of this Y of W dot in usual Deligne-Lusztig theory. And so the claim is that these varieties show up naturally in the above diagram. Okay, so let me just write it down. So for that, I just need one remark, is that this quotient here, G mod ad FB, you can write it very easily using the Lang isogeny as G divided by B, just acting by translation, divided by GF. And the map is induced by the Lang isogeny, so G minus 1 F of G. So the reason this works is that if I remove all the quotients, this map is a finite étale cover of group G fixed by F. So if I look at the induced map from G to G, that's a finite étale cover of group G fixed by F. So if I mod out by G fixed by F, I have an isomorphism. One says this is an isomorphism. And then I can look at the other action of B on the induced thing. And maybe I just want something slightly different. Just want to put the minus 1 here to match with two-state conjugation as I defined it. And I mean, that's kind of, I wrote it with B that works with any subgroup instead. Okay? Okay, and so now, so let's plug this in this diagram. So if I take a single Brouwer stratum BWB in G with all these quotients, so I can look at the inverse image in G divided by ADF of B, and under this isomorphism, it just becomes very easy to see that this is y of W dot divided by, by G fixed by F, and by T fixed by WF here. Mapping to G divided by ad minus of G. And so here, this is identified with G fixed by Frobenius of G. And so this map is just induced by the pushing this y of W dot to the point. And the other one, so this quotient stack here, one should choose this point W dot, which lies in here, gives a base point for the, for the action of these two copies of U's and of T, and identifies with point mod T fixed by WF semi-direct U intersect with WU. And so kind of this, basically this variety Y of W dot mod the two quotients gives you a correspondence between the two categories of representations, and that's exactly the usual construction in Deligne Lusztig theory, because usually what you do is you take this variety, you say it has these two actions, its cohomology is a bimodule, and you do an induction functor. And exactly what we're doing geometrically here, we have a representation of the torus, which we see as a sheaf on this quotient, pull it back to the middle guy, and then push it forward. That's just the induction. OK. All right. And then so the one, there's one more piece of things, one more thing I said yesterday, which I still need to explain. So, so I said in the Heike categories, there are these objects delta W. And so it goes as follows. So on BWB mod U, so we can take sheaves on this. It's a full subcategory via the inclusion, so via the lower Schrick inclusion into sheaves on G mod U. And then I can complete monodromic both guys. And so this thing here, again, choosing W dot gives you an isomorphism with sheaves on maybe the torus times W dot. So non-canonical, it depends on W dot. And if you recall, this was some kind of QCO on some disjoint union of all the completions of T-Chech at all the torsion points. And so we can take the structure sheaf here, send it to an object LW, which is here, and which is something we want to call the free monodromic sheaf on this thing. So it's, and so I'm using the formal completion here, like the QCO on the spectrum of the formal completion instead of the INCO on the SPUF definition of the formal completion, which is just the difference between free and co-free in what happened yesterday. And we have this object delta W, which is JW lower Schrick of LW, shift by the length, which is just to make it perverse. And, plus, sorry, I think plus DMT. And the link with the thing before is that, so that's a thing on G mod U. And when we average it along this quotient map here to add f of t, this pi lower Schrick of delta W, so is a sheaf on this quotient here, and it corresponds to the regular representation of T fixed by WF. Okay. And so kind of all of the usual machinery of Deligne-Lusztig theory just kind of exist naturally in this above diagram, in this above correspondence, and kind of basically all of the usual constructions in the theory will work kind of just as is with this correspondence. Other questions so far?
So this L building is really huge, right?
Yeah. So it's
this high lower shriek is annihilating some massive part of it, right?
absolutely. Yeah. So L is a really big thing. So I mean, yesterday for the co-free one, you had on GM, you had a sheaf whose stalks were Q double parenthesis T mod Q double bracket T. So that's a really, really huge infinite dimensional QL vector space. I'm using the free one, so I would get QL double bracket T, which is kind of just a dual of the other one. And this averaging procedure here like really kills away most of this formal completion and it gets you something that's finite dimensional in the end.
So this isomorphism you wrote down on the left-hand side, so the bottom one is essentially the definition, right? And the top one?
Where, sorry, which one?
The ones on the left, between the sheaves, monodromic sheaf category.
Yes. Here?
Yes.
Yep.
So bottom one is essentially the definition, I guess, and the top one?
So the top one is just that BWB, mod U mod U, is the same as T times W mod some, this U intersect WU, which is a unipotential, which is not going to do anything. So you can just remove it. I mean, the only thing it's going to do is just shift away the perverse T structure. But apart from that, it's not going to do much. Yeah. No, that's purely like kind of just geometry of the thing. But the point is that I'm saying, okay, you had this map. So sorry, from the starting category, which is this Heike category, into its trace, and it's controlled by this above geometry, by this right below, like this geometry that appeared in this correspondence. And this is something I really want to do because, okay, I'm telling you, okay, this categorical trace is blah, but kind of you want to be able to compute with it and to compute stuff in this, and that involves kind of unraveling kind of the geometry that controls these things. Yep. Okay. Okay, and so just I want to say one more thing about the parabolic version of this. Which we can obtain as well. So, so for the classical Deligne-Lusztig construction, so what you consider is, so we have our borel that's fixed. We're going to choose, torus, a torus and a levy here. And so I will work kind of with standard parabolics and standard levies. So we do not assume that neither P or L are stable under Frobenius. But we're going to choose some V in the Weil group such that add V composed with Frobenius preserves L. And that's kind of really just the generalization of saying, okay, you want to look at the morphism W times F acting on the torus. For the levy, you want something like this, and so you cannot always assume that the levy is stable under such kind of automorphism. Okay. So, right, and then so attached to this, you can define y of p comma v dot again for a lift, which is going to be the set of G in G mod. So UP will be the unipotent radical of P. That G minus 1 Frobenius of G lies in UP V dot Frobenius of UP. And it's a thing that carries an action of G fixed by F and of L fixed by V dot F. Here. Okay, and so it's a variety that carries an action of these two groups, and so you can play the same game. You can take the cohomology of that thing, that's a bimodule for these two groups, and so you get an induction functor between the category of representations of the Levy to the category of representation of G. And so this we can realize this functor in terms of traces. So what you have is that you have the Hecke category for G, and you have the Hecke category for the Levy, and you have an inclusion here, which is going to depend on the parabolic. And this is some kind of sheaves on G mod U completed monodromic, sheaves on L. So UL would be U intersected with L. And IP is induced by the usual parabolic induction diagram. Okay, and so it's not hard to show that this IP is monoidal, compatible with Frobenius in a reasonable sense. And then so you can define a similar subcategory. So I have chosen my P and I have chosen my my element V in the Weil group, and can take just the subcategory of sheaves on the double coset P, V, comma F of P. Sorry, but this. So completed monodromic. And it's a subcategory which is in the full Hecke category of G. And it's a category that is stable under HL, acting by either left translation or right translation composed with Frobenius. Okay, so that thing here, so what I'm saying is that HPV is an HL bimodule. So what you can do is, now you have a monoidal category, HL, you have a bimodule for this, so you can take the trace on the two category of HL modules induced by this bimodule, which is kind of the pattern we first considered when we took categorical traces on the category of modules over something. So we can consider the trace of HPV. So maybe let me also add kind of, there is implicitly a Frobenius here on the right, because so I'm taking sheaves that are supported on F of P for the right coset, and so to be stable under HL, I need to first send HL into H of Frobenius of L, and then just act on the right here. So there's a Frobenius implicitly lying around here. Okay? On HL mod, here. Okay, and the theorem is a generalization of the previous theorem that computes the categorical trace, is that this is equivalent to sheaves on PV F of P divided by, so UP at Frobenius of L, and this thing here is a variant of the previous quotient, and it's isomorphic to point mod L fixed by VF semi-direct. This thing here, which is again a connected unipotent group. Okay, And then there is a well-defined map of pairs. Here, so should put mod here and here. So induced by the following thing. So you have an inclusion of HL into HG, and so that allows you to view HG as an HL module, and it induces a functor from HL modules to HG modules. So the first thing here is induced by HG viewed as an HG, HL module. So that gives you the functor between the two categories of HL modules to the two categories of HG modules. And then, so you need, to have a morphism of pairs, you need a commutative diagram between the morphisms. And so the morphisms are induced by these two guys here. And if you unwrap the diagram, this is just the inclusion of the corresponding stratum P, V, Frobenius of P inside of G. So just, sorry. The inclusion of H, P, V in H, G. Okay, and so the second part of the theorem is that the induced trace of this morphism here, so HJV lower Schwick, as a map of traces between these two things, so is the functor. So it's the functor given by usual parabolic Deligne-Lusztig induction, and you can write it geometrically as follows. So you have this quotient here, from P into this quotient, and again, kind of the same diagram as before. So this is y of v dot p, so the parabolic affine Deligne-Lusztig variety divided by gf and by L fixed p by v dot f. So it's the same diagram as before, but in a parabolic version. And so let me kind of just say one last thing here is that, so there is some kind of intermediate guy that shows up here, and it turns out that this was studied, like sheaves on this gadget here were studied by Lusztig around 2006, and they, like sheaves on this, they bear the name of parabolic character sheaves. So. Like this. And kind of the link in terms of traces is that you can view HG, so the full Hecke category of G, as an HL bimodule, and sheaves on that thing is, and so the third point of the theorem is this is trace of HG twisted by, yes?
I'm not sure you finished your thought. You said something is the functor, and then you drew a huge diagram.
Oh, sorry. I mean, okay, so it's a functor, so you have J, V here, alpha p, beta p, thank you. And it's the functor, so given here by JV lower Schwick, alpha p lower star, beta p lower Schwick here. And it's kind of really just the analog of what was happening in the Borel case. Thank you, thank you. Yeah, and so kind of just to finish the statement, that kind of this intermediate guy shows up also in terms of traces. And so when you view the HG as an HL bimodule, and so it's kind of the thing that contains everything. And I'm doing here everything at the level of like finite dimensional group schemes or finite dimensional reductive groups. I think Xinwen is going to talk about the affine version of all these things next week. And so kind of, there's a whole yoga of these things, but it's always the same kind of yoga that shows up here. So kind of, it's a good way to kind of just warm up. Yes, please. Where?
So yeah, there is an arrow from HF, HFTV to HGF. So I was wondering what does the arrow
Sorry. Can you say it louder?
So there's an arrow from HFTV, HM1 to HGF, HG1.
Uh-huh.
So yeah, what does the arrow actually do?
Yeah. So remember to write the functionality of traces, right? So kind of you have a category, which is here HL mod or HG mod, together with an endomorphism. So for one of them it's the thing given by the bimodule HPVF, and for the other one is the one given by HGF. Okay? So you have like two categories with an endomorphism, and to write the functionality of traces, what you need is you need a map between the categories. So here you need a map between HL mod and HG mod. So that thing is given by a bimodule for HL and HG. And the map that gives you this is, so you have this inclusion from HL to HG, and you can view HG as a bimodule over these two guys. That's the map between the categories. And then you need and so if you remember, I had like, you need to write a square, and you need the natural transformation. Okay, and so that natural transformation is just provided by the inclusion of this HPV into HG. Yeah.
So the trace is taken in the more rated two category.
Correct. So we're taking the trace on a two category. So so kind of we're taking the trace in 2 PRL, and kind of like this Morita 2 category lives inside 2 PRL. Yeah, absolutely. Any more questions? Okay. All right, so that was kind of where I wanted to end up yesterday. And so kind of to kind of now kind of compare a bit more, so to kind of switch topics slightly, and I'm going to come back to this example right after. So I want to do like this comparison of 1 categorical traces and 2 categorical traces. So kind of like we're searching topic for a moment, and then we're going to go back to the example. So here's the setup. So we have a monoidal category, together with a tensor endomorphism, F. And then we can do 2 things, right? And these are the 2 things we've really been looking at so far. So we can either take A mod, which is now a 2 category, with an endomorphism induced by F, and we can take the trace of F on A mod. Okay? And that object is a category. Or we can take A, viewed as a plane category, take trace, which I'm going to write as small trace versus a big trace, to kind of distinguish them as, like, one is a category, the other is a vector space or an algebra or something, of F on A. And so that thing is a priori only a K vector space. Okay? But you recall that the trace is a symmetric monoidal operation. So trace of F1 tensor F2 on A tensor B is the same as trace of F1 on A tensor trace of F2 tensor B, of F2 on B. And so that symmetric monoidality tells you that the trace is an operation that will send an algebra, namely a monoidal category here, onto an algebra. Maybe on an algebra. And so that thing here really lives in the category of algebras in vect, so it's something you can take. And so what we can do is we can take trace of f on A mod. Okay, and so the game now is to compare these two things. So these two objects now, they are two one categories, okay? And basically the difference between them is you've switched this parenthesis here over there. Okay, but usually like doing certain operations don't commute with like moving out the parenthesis. Yes? Okay, and so I think I have not said what is the definition of a rigid monoidal category so far. So let me recall the definition. So for my sake, I will assume that categories are compactly generated. So we'll take A to be a monoidal, compactly generated category. And it says that A is rigid. Oops. So if, at the beginning, so in the first lecture, I defined the notion of dualizable object, and I said, okay, we're doing this in symmetric monoidal categories, so it doesn't matter whether we do it on the left or on the right. In a genuine monoidal, not necessarily symmetric monoidal category, we need to enforce, to distinguish between left and right dualizability. So, but you can imagine the definition by switching where you put the dual for the tensor product. So every compact object is left and right dualizable, left and right. So you can look at the multiplication map. So let me write the tensor operation on A as a convolution to distinguish it from the tensor of categories. It's continuous right agent. Which here, oops, means that convolution preserves compact objects. And I want the unit in A to be compact. Okay, and so kind of all of the examples, I think, or almost all of the examples I looked at so far of monoidal categories were rigid. So example of such, so you take X to be a quasi-compact scheme, then QQ on X is rigid, and or you can take H, the Hake category as before, the free monatomic. Okay. All right, and so here's the theorem. No, sorry. So before the theorem, I want to say one more thing. So, yeah. So, okay. So now we're going to take A to be a rigid monoidal category. Okay, together with the tensor endomorphism, F. So we can form the two-category trace of F on A mod. And as we said before, so it's a category that receives a map from A, okay, which again is this A tensor A, F over A tensor A rev, and the thing that sends X to 1 tensor X. Okay? And so there is a description of this functor just in terms of the Chern character, which I talked about in the first lecture. So let me recall. So the data of a Chern character. So to talk about this, so we fix the following data. So we fix M to be an A module. And then we needed some kind of compatibility between M and the Frobenius. And so we needed the datum of a morphism. Sorry, I need to be compact. So I will assume that so I will assume right dualizable as an A module, which is, so to define these Chern characters, I need to take a compact object here. I will assume this, and since A is rigid, it's equivalent to the fact that M is dualizable as a plane category. So write them as an A module. As a plane category. Okay, and I need to give myself a morphism from F to F upper star of M. Okay, and then, so from this, so that data defines you, so let's call this alpha, defines you a class of M comma alpha in the big trace of F on A mod. And so now we can take X, if we take X to be an object of A, we can define so M to be the category A viewed as a left A module. Okay, and we can define the map alpha from so A to A to be the morphism which sends Y to F of Y times X, where you multiply on the right. And so that thing is a morphism of left A modules. Okay? All right, and so here's a lemma, which is a rather immediate calculation. So there is a canonical isomorphism so in the category trace of F on A mod. So between, so on one side, so the object T of X, where T is again this map from A to trace of A on A mod, and the class of A and this morphism alpha that we defined above. Oh, sorry. Yeah, I should mean convolution. Yeah, thank you. So I mean the multiplication in the category A. Yeah, thank you. Yes, because you need to map to F of M. And so you need to apply f somewhere. Yeah. All right. And so here's a theorem, and the point of the theorem will be to allow us to compute endomorphism algebras, at least certain endomorphism algebras, in the category trace of f on A mod. So theorem, which I think I read about it in this paper of Gatsgary, Kashdan, Raskin, and or Rosenblum and Warshawski, which is called, I think, a toy model for the Infeld-Lafforgue shtuka formalism, or something close like this. So it says the following. So again, A is rigid. One category with an endomorphism. M is an A module, together with a morphism alpha from M to f of M. So, and the theorem says two things. So you can look at the object T of the unit of A. So that is an object in trace of f on A mod. And the statement is the following. So there is a canonical isomorphism of algebras. There exists an isomorphism of algebras between the endomorphism of that object in the two categorical trace and the one categorical trace. So this is really the thing that links the bigger trace, the trace on the two category of A modules, with the trace on the smaller, on just the category itself. Yeah? And the second point is that if you take hom from T of 1 into class of M alpha, so that, again, is a vector space, and it's the, so it's the same as a trace of alpha on the category M. So what this means is that the morphism alpha, I've written it as a map from A to f of M, from M to f of M. F of M is, as the underlying category of this, is just M. F of M just changes the A module structure on it. So it's the same category, just changing the A module structure. So this trace of alpha on M makes sense because alpha is an endomorphism of M, of the underlying category of M. So, sorry, what?
We're assuming M is dualizable.
Sorry, thank you. So I should say yes. So M is dualizable. Yeah, thank you. Which, like, so I just said just a bit before that is the same as M is right dualizable as an A module, which is what you need to be able to form this class. Okay, so now we can breathe for a second because, like, now I will just apply this theorem to the three examples we had before, and I think then I will run out of time. So, and I just want to say, so that theorem is also kind of one of the critical points that is used in this paper of Bezrukavnikov, Shenhan, and Nadler. So let me give an example for this. So we can take, take A to be QCO on X for X, a finite type scheme over K. So now let's kind of recall what we said before. So we said first, the trace of the identity, so I'm going to take F to be the identity for this, on A mod, here was QCO on, so loop stack of X, which is, recall, loop stack of X is X times X over X times X. The map from QCO X into this thing here, so it's pulled back along one of the projection. Along this. And the small trace of identity on QCO X was Hochschild homology of X, which is the same as global sections of the loop stack of the structure sheaf, evaluated on the structure sheaf. So, okay, and so that here is an instance of the first point of the theorem. So, right? So, if you take 1 in QCO, that's the structure sheaf. So you take the structure sheaf here, you put it back to the loops of X, that's again the structure sheaf on this more complicated object. Its endomorphism is just cohomology. Okay, that's what we find here. So that's, at least that works in that example. Okay. Okay, and so the second example I want to do is the Hecke category. So take H to be the Hecke category, the free monodromic again. Okay, and then so trace of Frobenius on H mod, as we said before, is sheaves on point mod GF. The image in 1 in H here, so it's the Deligne-Lusztig variety attached to 1, which is just the parabolic induction from the Borel, so it gets sent to of 1. Okay, and the morphism of that thing here is okay. It's the, sometimes people call this the monodromic Hecke algebra. I'm just going to write it. It's a Hecke algebra. And then, so if you recall, so in the first lecture, I kind of gave you the example of trying to compute the trace of Frobenius just on the category of sheaves, not on some two categories, but just on the category of sheaves on some scheme X, of L-adic sheaves on some scheme X. So the formalism works very similarly for stacks. And so I'd said at this point, so kind of the trace you get might be just not the correct object, and that was because the QNet formula didn't hold. One of the things we fixed by passing to this monodromic category is the QNet formula. And so it's going to be true on the nose for this Hecke category that the corresponding trace here is the corresponding Hecke algebra. And that's via the function shift dictionary. And local term of lecture 1. Here, so kind of there you get kind of a very complete picture of these things. And so, yeah. Yeah, and so kind of, if you want, you can push even further. So kind of I've computed the endomorphism of 1, or the image of 1. I think I said before that one of the open questions in Deligne-Lusztig theory is to compute the endomorphism of the cohomology of other Deligne-Lusztig varieties. We kind of expect that this is a good way to try to access it. But for now, this is still open. And, right? And so also to link up with David's talk of yesterday, so I've taken this trace on the finite Hecke category. If you replace by the affine one, you're going to get the corresponding statement for the affine Hecke algebra as trace on the affine Hecke category. Okay, and then so kind of let me just mention like further applications to kind of this Deligne-Lusztig theory world of these categorical traces. So further applications. Deligne-Lusztig theory, and presumably next week, Xinwen will explain the applications to PID groups, to representations of PID groups of these traces. So, can prove endoscopy for modular representations of finite groups. Finite groups of Lie type. And so that is very much due to Lusztig-Yun in characteristic Zion over QL. And myself, I'm going to say 26 because the update to the paper is coming soon, mod L. So another application is the independence of the parabolic. For Deligne-Lusztig induction. So for the Borel, it is in the original paper of Deligne-Lusztig. And then kind of for a Levy, for a general parabolic, so when Q is large enough, it was due to Deligne, and I think, no, sorry, it's both Deligne and Lusztig in some later paper. Up to some work of Bonafé and Michel in 2013, using a case-by-case analysis, and I mean, it's kind of visibly not the correct method, and or not the most satisfying one, maybe. And a full proof of this was established so by Getzgering, Rosenblum, Warszawski in their paper, which has appeared a few times already. And that was kind of for them the main motivation to write that paper, so 26. And then maybe let me mention a future application of this thing. So something called the genericity. And so it's formally, so it's been formalized by Brouet, Michel in the 90s. And it's kind of the formal notion of the following observation that we make, that when we take our finite groups of Lie type and we look at the unipotent part of the representation theory, it turns out that all the numerical constants, so like the dimension of unipotent representation, the number, the cardinality of the group, character values, and so on, they kind of don't really depend on Q's. They're all polynomials in Q. And so there's, I mean, one of the few things that we should do is, that, or rather that we're doing, is to provide a categorical explanation to this fact. So, sorry. In Q. And yeah, I mean, and then you can imagine like there are other potential applications that we can continue to go on. So, but I think I am running out of time, so I will stop here. Thank you.